Okay, so we just saw a demonstration that introduced something called the buoyant force. So when you submerge an object in a liquid, or in a gas actually, there's an upward force. Okay, there's an upward force, it's called the buoyant force. Now, this is explained by Archimedes' principle. Here we go. When a body or an object is completely or partially immersed in a fluid, the fluid exerts an upward force on the body equal to the weight of the fluid displaced by the body. So the buoyant force, FB, equals the weight of the fluid displaced. But again, come on, usually when you're dealing with like a liquid, you don't know what the mass is, you know what the volume is. So, you know, what did we learn the other day? Density is mass over volume, so therefore mass is the density times the volume. We're going to use this a lot. So here, instead of having mass, we just use the density times the volume of the fluid, right? This is the density of the fluid. It's not the density of the object. I don't care about the object. It's the density of the fluid, the volume of the fluid displaced, and you know, G is G. So this is kind of a nice little diagram. So here, you know, this is something that measures the weight, and it's measuring the weight of this thing, and it's 3 whatevers. And then here, this is empty. So then, this thing is submerged in the water, and the weight goes from 3 to 1. So it decreased by 2. Well, what happened to that 2? It's the weight. See, this thing, you know, this was full, correct? So when you put this inside, some of that water has to go out. So this thing displaced this much water. And the buoyant force is equal to the weight of the fluid displaced. 2. Okay? Great. Yeah, here's something else. All right, so this is the rho, which is the density of the fluid. Okay, so G is just G, right? So you pull out the G. Then rho is just rho fluid. Now, the volume of the fluid displaced, isn't that just the volume of the object submerged? Well, yeah. I mean, if it's completely submerged. All right? So there's different ways to write it. This is probably the most useful way to write it. Okay, so here we go. All right? So the buoyant force, I'm repeating myself. The buoyant force is the weight of the fluid displaced. This is the weight of the fluid displaced. Now you have rho v, fluid displaced, G, rho fluid, volume, object submerged. And again, what did we see? Experimentally, we saw that the buoyant force does not depend on the depth. Remember, I lowered it, and the buoyant force didn't change at all. Okay, very good. Now, why do we have a buoyant force? Why do we have a buoyant force? Well, we learned in our previous class that the pressure increases, right, with depth. And so this is less than that. And so there's a net upward force, right? And that net upward force is just that buoyant force. But we also learned that the pressure is linearly dependent on the depth. So let's say we have an object that's a meter, okay, a meter high. So we want to calculate the pressure at 2 meters compared to 1 meter, okay? And so, you know, you're just going to put in 2 meters and then 1 meter and subtract. So this goes away. So the pressure at 2 meters minus the pressure at 1 meter is just rho g, 2 meters minus 1 meter, which is just rho g times 1 meter. Okay, so let's say we have a big swimming pool, all right, and the depth was just 2 meters right near the surface of the water, you know. But now, let's put it deeper. So now we want to calculate the difference in pressure at 11 meters and 10 meters. Well, you just do the same thing, right? You just plug in. So the P zeros go away. Rho g 11 minus 10, you get rho g 1. Okay, now let's make it super deep. So 100,001 meters at 100,000 meters. So it's super, super deep, right? Super, super, super deep. But again, the distance is only a meter, and so it's rho g times a meter. All right, so it doesn't depend on where the object is located. Okay, here it was near the surface. Here it was a little bit further down. Here it was way down. But you can see that the pressure is independent of the depth, which is what we saw. And again, that's because this is linear, right? It's linear, okay? Yeah. All right. Okay, so here's an experiment, which we're not going to do. So this is a beaker full of water. This is a solid sphere. It's going to float in the water. So what I want you to do, please, is draw the force diagram and write the force equation. So pause your video and do that. Okay, so we're back. So what are the forces on the sphere? Well, there's the weight, right? And then there's just the buoyant force. And it's in equilibrium, so the buoyant force equals the weight of the object. I'll be careful. The weight of the object. Okay? All right. Now what I want you to do is what it says on the top there. Determine what fraction of the sphere's volume is submerged. So everything you need is here. So pause your video and please figure out what fraction of the sphere's volume is submerged. All right, I hope you've done that. Let's work it out. All right, so we saw that the buoyant force equals the weight of the object, right? Because it's in equilibrium. Okay, now let's work on the buoyant force. So the buoyant force, by definition, equals the weight of the fluid displaced. Okay, so I'm lazy. I'm not going to keep writing fluid displaced. I'm just going to write displaced. Okay, so if I write displaced, it means the fluid displaced. Okay, all right, so that's just the definition of the buoyant force. And again, the mass of the fluid is rho v. So we're going to have G rho v, fluid displaced, okay? And that's just G times rho fluid displaced times the volume fluid displaced. Now, isn't volume of the fluid displaced the same thing as the volume of the object that's submerged, right? Same thing, right? Okay, all right, so that's true. Now, let's work on the weight of the object, okay? So the weight of the object is m object g, but let's say, all right, what's the mass of the object? It's the density of the object times the volume of the object, so times g, okay? All right. So now let's use our results and put this equal to that. So we can get rid of the g's, right? Cancel out the g's. So we're going to have rho object, v object. I can put submerged though, right? Because it's only the volume of the object that's submerged, right? That's displacing the liquid. Whatever here, sorry. Sorry, I screwed up. Okay, I want to do this first. So rho displaced fluid times volume submerged object equals rho object times volume object. That is totally correct. All right, now we want to get the fraction of the sphere's volume. So therefore, just do a little division. So let's just, all right, so we'll have volume submerged divided by volume object equals rho object over rho displaced. Okay? So the volume that's submerged divided by the volume of the object, right? So we're talking about the fraction of the sphere's volume that's submerged equals the density of the object divided by the density of the fluid. And I promise you, if you plug in all these numbers, you get 70%. Okay? So that's just an example of how you do these kinds of problems. So, I mean, study this. You should do it by yourself. Make sure you get the right answer. All right. So, okay. So here's a question for you. If an object immersed in a fluid sinks, what's true? So pause your video and vote. Okay, we're back. So obviously, if this thing sinks, this force is greater than that force. So that means that the weight of the object is greater than the buoyant force. No kidding, right? The weight of the object is greater than the buoyant force. That's physics 121, right? Physics 121. Okay, so what we want to talk about now, though, we want to talk about floating, submerging, sinking, all that kind of stuff. So what we're going to see whether or not an object floats or sinks or whatnot depends on the density of the object and the density of the fluid. Okay, let's do this one. So we want the buoyant force is less than the weight of the object. All right? Well, that means, okay, what's the buoyant force? It's the weight of the fluid displaced. So if this is true, we have the weight of the fluid is displaced. The weight of the fluid displaced is less than the weight of the object. Awesome. All right, well, what does that mean? It means mg, fluid displaced, is less than mg, object. Well, what does that mean? Okay, well, first of all, get rid of the g's, right? So that means that the mass of the fluid displaced is less than the mass of the object. Now again, we typically don't know the mass of the liquid. So let's change it. So that means that rho v displaced is less than rho v object. Agree? But come on. This thing is it's immersed in the fluid. So isn't the volume of the dispersed fluid equal to the volume of the object? Well, yeah. So that means that the density of the displaced fluid is less than the density of the object. Okay? So there you go. All right? So if an object immersed sinks, it means that the density of the displaced fluid is less than the density of the object. Or you can say that the density of the object is greater than the density of the fluid if it sinks. All right? Now, here. If an object immersed in a fluid rises, what happens? So, pause your video and answer the question. Okay, it's obvious, right? If it rises, then this force has to be greater than that force. So it has to be that the buoyant force is greater than the weight of the object. And you can do this whole argument again, and you will see that if this is true, that the density of the displaced fluid has to be greater than the density of the object. Okay, if an object immersed in a fluid has neutral buoyancy, that means it doesn't rise or sink, the acceleration is zero. What's true about the forces? Well, again, physics 121, right? Equilibrium, that has to equal that. So the buoyant force equals the weight of the object. You can repeat that, and you'll see that the density of the displaced fluid equals the density of the object. Okay, have anybody ever seen this stuff before? Apparently it used to be popular in Utah years ago. It's a soda pop, and they put these little edible beads in it, and they have the same density as the soda pop. So they just stay there. You know, they don't rise, they don't sink. And when you're drinking your soda pop, you can drink these things and it doesn't harm you, I guess. Apparently they don't sell it anymore, so it must have freaked people out or something. I don't know. But okay, there it is, all right? The density of the displaced fluid has to equal the density of the object. So these things have the exact same density as the liquid. Okay, here's a question for you. What will happen to a neutrally buoyant object if its mass is increased by 1%, but the volume doesn't change? So everybody, pause your video and figure it out. Okay, we're back. All right, so look, density is mass over volume. So if the mass increases, but the volume remains the same, what happens to the density? Well, obviously it increases. If the density of the object increases, what's going to happen? It's going to sink, right? Because now the weight of the object is greater than the buoyant force, so it sinks. Okay, one last question, for a while anyway. Consider the three suspended objects in the figure. All three blocks have the same size. That's important. This mass equals this mass, but this is the heavy guy. So compare the scale readings. So pause your video and figure it out. Okay. These have the same size and the same mass, so they have the same density. This one, they all have the same size, but this one has the greatest mass, so that means it has the greatest density. Agree? Agree? It has the greatest density. Okay? So that, all right. All right, any questions? Okay. All right. Oh, I got to do another demo. Oh, this is a fun one, too. Let's see. All right. Okay. Anybody see a piece of aluminum foil around? What did I do with my aluminum? Oh, there it is. Thanks. Thanks. Okay. So I'm going to make a little boat out of this sheet of aluminum. Not very fancy, but I don't care. Okay. So there's my boat. Pretty impressive, right? Okay. What does it do? Floats. Very nice. Now I'm going to take my piece of aluminum foil. And I'm going to make it small. I guess that's... All right. I think that's good enough, right? That's what happens to students that don't do their homework. Just kidding. All right. Now look it. I didn't change the mass or anything, right? Okay, watch. What happens? Does it float anymore? Nope. Doesn't float anymore. It sinks. What's going on? So, you know, the weight of the object didn't change, right? The weight of the object didn't change. But what changed? The upward buoyant force, okay? So in other words, the boat displaced a lot of water. But when I smash that thing, how much water does that displace? Not so much at all, right? So the weight of the object didn't change, but the buoyant force changed. Okay? All right, so let's do something. Okay, so for the floating boat, what's the force equation? Well, the upward buoyant force equals the downward weight of the object. Agree? Okay. And now, what's the buoyant force? It's the weight of the fluid displaced, right? Okay. So therefore, what can we do? We can say that the weight of the object equals the weight of the fluid displaced. Okay? Now, what's another way to say that? Another way to say that, this is floating. Yeah, make sure, right? This is floating. Agree? Okay, so another way to say that is this. Oh, so that's what I just demonstrated. Just pretend this is aluminum foil, all right? This displaces a lot of water, so there's a large buoyant force. I mean, the weight is the same because it's the same object, but here this doesn't displace much water at all, so it's a small buoyant force, right? Okay, so something that floats, right, the floating boat, the weight of the object equals the weight of the fluid displaced. What does that mean? This is what it means. It means floating objects displace their own weight in a fluid. That's what it means, right? So the weight of the fluid displaced equals the weight of the object. That's important, okay? So floating objects displace their own weight in a fluid. So the weight of the displaced fluid equals the weight of the object. Okay, you're familiar with a Goodyear blimp? Why is it so large? Well, first of all, it's floating, correct? Now, it's floating, so the weight of the object has to equal the weight of the displaced fluid. Whoa! So we're talking about air, right? So that means that this blimp, if you took all the air that it is displaced and you calculated the weight, that would equal to the weight, that would be equal to the weight of the blimp. Okay? So that's why it's so large, because, you know, I mean, air doesn't have a lot of density, right? So the weight of this big honking Goodyear blimp equals the weight of all that air that it's displacing. Okay? Okay, a 10,000-ton ship must be built wide enough to displace how many tons of water? So pause your video and figure it out. All right, so we're back. And what did we learn? You know, we learned that floating objects displace their own weight in the fluid, right? Say it again. Floating objects displace their own weight in the fluid. So here we have a ship. It's floating. Floating objects displace their own weight in the fluid. If it has a weight of 10,000 tons, it has to displace how many tons of water? 10,000. Okay? That's all there is to it, 10,000. Okay, let's quit. Let's stop this video.